Hello, my work is about large-scale phenotyping using tensor factorization on Apache Spark. The goals are twofold. First is to parallel tensor decomposition on Spark platform, and then to discover useful phenotypes for large-scale data. Let's see the background. The sparse tensor can be interpreted as a multi-way array. This is a third-order sparse tensor with the non-zeros marked as dots. There are several tensor operations. In this work, we focus on the matrixized tensor times Cauchy-Rho product, MTT-KRP, which is a bottleneck of CP decomposition. So CP decomposition decomposes a tensor as a sum of component rank 1 tensors, and the rank here we use R to represent the rank here. CPD is an important algorithm for phenotyping. The algorithm we used here is CPELS. CPELS algorithm takes the nth order sparse tensor as input and a given rank R, and the output is a sequence of factor matrices. So there are one while loop and one for loop here, two iterations. The two main steps are here. The first one is a Hadamard product sequence, which can compute all the matrix multiplication and do the Hadamard product to generate the matrix V, and the second is do the MTT-KRP operation. So let's see our parallel CPLS algorithm. First, we designed three main data structures for sparse tensor. This is a third-order sparse tensor in coordinate format. So for each line, represent a non-zero with a value and its indices, three indices. And the SP10 tuple is a class to represent each non-zero. And SP10 and SP10 RDD represent the local sparse matrix or a distributed sparse matrix, with the three other members to represent number of dimensions, number of non-zero entries, tensor size. And then for a local tensor, we represent using array, and for distributed tensor, we use RDD format to distribute the sparse tensor. Now we get the parallel MTT-KRP algorithm. There are two loops per 4 here. So the first parallel section, the main operation is to compute each non-zero entry from the sparse tensor with a dense vector from the matrix, and then generate a dense vector stored in Y. After this part 4 section, we get the intermediate tensor Y, and then we use Y to do a element-wise product with the matrix B to generate a matrix MA. And then let's see the parallel ALS. Besides the parallel MTT-KRP algorithm, we also do an optimization on the updating way here. So for each time, we don't compute each AI and times AI, and we only compute the update one and then do the Hadamard reduction. But instead, we stored all the results here. So, but actually, each matrix generated here is very small, so it is not expensive. So let's see our experiments. We compared 4 implementations. The first two PWAG and SWAG are our parallel algorithm and our sequential algorithm. And PINIT and SINIT means parallel in the most straightforward algorithm in parallel or in sequential. We test on 2 datasets. The first is a synthetic sparse tensor generated by Tensor Toolbox. It is very small tensor, and the other is a mimic tensor generated from Mimic 3 dataset. So for the small dataset, we can see our algorithm, both parallel or sequential, get good speed up compared to the most straightforward algorithms. But we don't show much speed up in parallelism. Also same here on mimic data. This is a sequential running time. This is the parallel running time on Spark. So the running time actually worse. Parallel running time is about 2 times worse. And for here, because the data set is large, the most straightforward algorithm is very space consuming, so it cannot test any results here, it cannot run here. So we analyze there are 2 reasons. One is we use expensive matrix transpose, especially here in the algorithm, because the Breeze stores the matrices in column major format, and we need to do each row. So we do a lot of matrix transpose. And another reason is maybe the mimic data is out of memory. So we also compared the different ranks, and our algorithm is quite stable, means it is possible to compute more phenotypes each time. And then we observed our most genetic phenotype here. Our conclusion contribution is we designed a coordinate format for sparse tensor and build all the tensor operations, and we propose a parallel MTT-KRP and CPALS. And then though we don't get to speed up, but for large tensors who cannot resident in memory, we can easily handled by our algorithm. That's all. Thank you.